We all face it, right? Data overload. It feels like it's coming from everywhere now more than ever.
Hmm.
And whether you're a programmer trying to juggle millions of unique IDs or, just someone trying to structure the chaos of your digital life, the secret to speed really lies in the architecture.
That's absolutely right. It's not just what you save, but how you save it. The performance of any large-scale system is really decided at this fundamental level, the data structures you choose.
This is not magic.
No, not at all. Modern application speed is just a series of meticulously engineered performance trade-offs.
Okay, let's unpack this. Let's get right to the foundation. Today's deep dive is zeroing in on a cornerstone of computing, the data structure known as a set.
And specifically, we're looking at the two major types you'll find in systems like C++A, which are the ordered set, versus its hyperspeed cousin, the unordered set.
Right. And our mission for you, the listener, is to move beyond just knowing the names of these things.
Exactly. We want you to understand the specific mechanical differences, the underlying code architecture that dictates their performance.
And to do that, we'll be using official documentation and some real-world examples from competitive programming, like the challenges on Kattis, to show when raw speed really trumps meticulous order.
Sounds good.
So let's start with the absolute baseline. When we talk about any set container, whether it's ordered or unordered, what's the single, non-negotiable rule?
Uniqueness. That is the essential rule. A set is a collection of elements where every single element must be distinct.
No duplicates allowed.
None. If you have the number 5 in your set and you try to insert 5 again, the operation just fails silently. It's a perfect mechanism for enforcing that uniqueness.
Perfect. So let's talk about the classic approach first. The container known in C++ as std.set, or the ordered set, besides uniqueness, what's its defining trait?
It guarantees sorting. That is its defining feature. The elements are always maintained in sorted order by their values.
From smallest to largest, or alphabetically?
Right, and that guarantee means if you loop through the set, you know with absolute certainty that the sequence will be predictable.
Okay, but I have a performance question right away. If I have a set of, say, 1,000,000 unique items, and I want to insert a new one that belongs right in the middle, like between item 500,000 and 500,001, I just imagine reorganizing all of that to maintain the order must take a lot of time. So where does the efficiency come from?
That is a critical question, and you're right. If it were a simple list, it would be brutally slow. But the ordered set isn't implemented as a list. It's implemented as a structure called a red-black tree.
Ah, the famous red-black tree. It sounds almost mythological, but it's foundational to this. Can you give us an analogy for how this tree works?
Sure. Think of it like a perfectly organized, a meticulous library shelf. When you insert a new book, the red-black tree immediately performs these tiny local rotations and recoloring operations.
That's the red and black part.
That's the red and black part. And it does this to ensure the shelf or the tree remains perfectly balanced. No one side can get too heavy, and no single path to find a book can become overly long.
So it's constantly self-adjusting to keep the whole structure as sort of flat and wide as possible.
Exactly. And that self-adjusting balance is what ensures fast operations. This structure gives us what's called logarithmic time complexity, which you'll usually see written as O log n.
O log n. Okay, that's a crucial concept we need to break down. For the listener, what does that actually mean in practice? Especially when you compare it to, say, a standard unsorted list.
O log n is just brilliant because it means the time it takes to do something only grows very, very slowly as the size of the data that's n explodes.
Well, let's put some numbers to that.
Okay. If you have a list of 1,000,000 items, so n is 1,000,000, searching through it unsorted might take up to 1,000,000 steps in the worst case.
1,000,000 steps.
But in a perfectly balanced red-black tree, searching for that same item only takes about 20 steps.
20 steps versus 1,000,000. That's incredible.
And now scale it up. If your set grows to 1,000,000,000 items, the red-black tree still only needs about 30 steps. That logarithmic speed is the guarantee. It's highly performant while maintaining that strict sorted output.
So if my program's logic absolutely requires data to be in sequence, then the overhead of this red-black tree is more than worth it for that O log n guarantee. Where do we see this in practice?
You see it a lot in geometry or comparison problems. Take the Knight's Move problem, which is a classic pathfinding challenge.
Okay.
To search the problem space efficiently, you'd use an ordered set to track thousands of possible moves, specifically because you need them in sorted order to explore the lowest cost paths first. Order is mandatory for the algorithm.
Makes perfect sense for any kind of sequential searching.
And we also see it in set mathematics. The CD problem, it's about finding the intersection of two massive lists of unique catalog numbers. Calculating that is so much simpler and faster when both sets are already sorted. And same with the midjoin problem, which uses the ordered set for calculating set differences. Any comparison across collections is just sped up by that inherent order.
This all sounds incredibly robust, very reliable. But here's the challenge for so many modern applications. What if I don't care about the order at all? What if all I care about is whether an item exists, and I want that check to be as fast as mathematically possible? Which brings us to the trade-off, the unordered set.
Ah, yes, the structure that trades that guaranteed sorting for just raw, blistering speed. The unordered set makes that one massive sacrifice. It completely abandons the sorting requirement.
All for the sake of speed.
All for the fastest possible average time complexity.
So if it's not using a complex red-black tree, how does it organize its elements? How does it deliver those speed gains?
It uses a completely different technique.
Hashing.
Hashing, okay? Every time you insert an element, the container calculates a unique numeric, like a fingerprint for that element. That's the hash value. The container then uses that fingerprint to know exactly which compartment or bucket to place the element in.
So instead of carefully positioning the element in a sorted tree, the element's own value tells the container exactly where it lives. There's no comparison step.
Precisely. You skip that logarithmic search entirely. When you ask if an element is there, the system just calculates its hash, jumps to the right bucket, and checks. It's a direct access mechanism.
And that results in?
It results in the single most efficient performance metric we have in computer science. Lookup, insertion, and deletion all have an average time complexity of 0.1.
0.1. Constant time. We explained O log n, so let's explain this one. Why do programmers consider this the holy grail of speed?
0.1 is the programmer's nirvana because it means the operation time is constant. It doesn't matter how big the input gets.
So it doesn't scale with the size of the set?
Not at all. Whether your unordered set has 1,000 items, 1,000,000 items, or 1,000,000,000,000 items, the time it takes to check if a new item is present is, on average, exactly the same. It's essentially instantaneous.
That is truly astonishing. But I have to ask, if O1 is so much faster than O log n, why would anyone ever choose an ordered set? There has to be a catch.
There is, and that's the critical piece of insight here. It's why this isn't a black and white discussion. O1 is the average case.
The average case, okay.
The risk with hashing is something called a hash collision.
A collision, you mean like two different items getting the same fingerprint?
Almost. It means two different elements generate hash values that map them to the same storage bucket.
Ah, so they end up in the same compartment.
Right. And when the system has to handle multiple elements in a single bucket, it might have to linearly scan through that bucket. If you have extremely bad luck or a poorly designed hash function and all your elements map to the same bucket,
then you're basically back to searching through a list. So the worst case scenario for the unordered set is ON, slow, linear time.
Exactly. And that is a trade-off. The ordered set, with its red-black tree, gives you a guaranteed ceiling on performance, O log n. It's slower on average than O1, but you have insurance against a catastrophic performance failure.
While the unordered set offers blistering speed most of the time, but you carry that small risk of a slowdown if collisions happen.
That's the choice.
That clarifies it perfectly. So if raw speed is the absolute #1 factor, and you can accept that slight risk, the unordered set is the clear winner. What are the textbook use cases for this?
Any scenario with high volume, rapid presence checking where order is completely irrelevant. Think about tracking user activity. In the Instagraph problem, you might be tracking millions of unique followers.
You just need to know instantly, is this user ID already in the set?
Yes, not where does this ID fall alphabetically.
That makes sense for high volume data.
Or consider the be your row problem. It involves checking for unique songs in a massive queue. The only requirement is filtering duplicates. The unordered set is the obvious choice for pure speed there.
Right, and we also saw it in the guest list problem and chorus phrases. The goal is just confirming uniqueness fast.
They all rely on that lightning-fast O1 mechanism.
Okay, so let's synthesize this for the listener. We've got two mechanical routes. The self-balancing red-black tree giving you guaranteed O log n and sorted output, versus Hashing and buckets giving you average O1 speed, but with risks. How do we make that choice in a real application?
You have to define your primary constraint. Do you need that sorting guarantee, or do you need the highest possible processing rate?
Like in the shopping list problem, the final output had to be sorted for the user.
So the ordered set is mandatory there. Even if it's a bit slower, the requirement for correct sequential output trumps pure speed.
But if the task is just filtering duplicates, checking millions of IDs, in some high-speed internal loop, the unordered set wins every single time.
It does.
Now, there's one fantastic example from the source material that really ties these two ideas together, showing that sometimes you need both. The tag problem.
Yes, this is a perfect synthesis example.
Oh.
It's a simulation with hunters and shooters.
Right.
So in the simulation itself, the main processing loop needs maximum speed. You're likely using sets internally to track the unique IDs of the hunters and the cheaters.
For that internal work, the speed of an unordered set would be ideal.
It would be. But, and this is the key, the problem's specification doesn't end there. The final requirement is to print the sorted list of cheaters after the simulation is over.
So that's the architectural twist. You have a choice.
Exactly. You either accept the O log n penalty and use an ordered set for the whole simulation just to have that sorted output at the end, or
you optimize. You use the fast unordered set for the bulk of the runtime, and then at the very end, you transfer that unordered data into a structure that can sort it for the final presentation.
And that decision really hinges on which is worse, the speed penalty during the simulation or the overhead of one final sorting step.
It really shows that sophisticated problem solving isn't about just picking the single fastest tool. It's about architecting a solution that uses the right tool for each part of the job.
Speed for the internal processing, order for the external presentation.
And these principles go way beyond just sets, right?
Oh, absolutely. The same mechanical dichotomy applies to key value storage. The keyboard problem, for example, it involves mapping inputs to outputs. It uses an unordered map,
which leverages hashing for O1, access to a value based on its key. Same principle.
Exactly the same speed principle we discussed for the unordered set.
So, at the end of the day, it all comes down to the mechanism. Guaranteed sorting through the self-adjusting balance of a red-black tree, or near-instant access through the calculated location of hashing in buckets.
The foundational knowledge here is understanding that efficiency isn't just about fast hardware. It's dictated by the guarantees and the risks engineered right into the data structure itself.
And that leads us to our final provocative thought for you to consider. When you look at the architecture of the data you handle every day, the information you consume, the files you manage, where is order truly essential to maintain functionality? And where is raw, speedy access the only thing that really matters?
Where in your digital life do you require the guaranteed precision of a sorted ledger, and where would you benefit from the instantaneous, if occasionally chaotic, retrieval of a high-speed search index?